Standard 11 Chemistry Unit 4 Chemical Bondings and Molecular Structure Part 19. Last time we had discussed about molecular diagram for 14 or less than 14 electron system, and the second diagram is for more than 14 electron system. Here the order of energy sigma 1 is sigma 1 is, that means here the bonding orbitals, and the sigma anti-bonding, that means sigma anti-bonding 1 is means anti-bonding orbitals is less than sigma 2s is less than sigma anti-bonding 2s is less than pi 2 px equal to pi 2 py, that means here they have nearly about same energy, is less than sigma 2 pz is less than sigma antibonding 2 px equal to sigma antibonding 2 py is less than sigma antibonding 2 pz. That means here pi 2 px and pi 2 py, that means they it forms double bond, and here this for sigma the single bond is formed. Now let's see about the another concept, that is the stability of the molecule. The stability of the molecule is depends upon the Nb, that means number of electron present in the bonding molecular orbital. Here the stability of molecule Nb, number of electron present in bonding molecular orbital, and Na, number of electron present in antibonding molecular orbital. If Nb is greater than Na, then molecule is stable. If Na is greater than Nb, then the molecule is unstable. Or another condition, if Na is equal to Nb, then the molecule is unstable. From Nb and Nb we can easily calculate the bond order. Bond order is equal to Nb minus Na divided by 2, or in another word it is defined as 1/2 of the difference between Nb, that means number of electron present in bonding molecular orbital, and Na. That means here bond order equal to Nb minus Na divided by 2. Or here the difference is positive value. Here the Nb is greater than Na, that means here the positive bond order. If positive bond order, then this stable molecule. Or the another condition that we have already discussed here, if Na is greater than Nb, or Na equal to Nb. Na greater than Nb, that means here the negative bond order is unstable molecule, or here Na equal to Nb, that means here the zero bond order, then and then molecule is unstable. Now the second is nature of bond. If bond order is 1, there is single bond between the atoms, single bond. If bond order is 2, then and then the double bond is present between the atom. Here the double bond. If bond order is 3, then and then there is triple bond in the molecule. Now the relation between the bond order and the bond length. Bond order is inversely proportional to bond length. Bond order is inversely proportional to bond length. And the another relation is bond order is directly proportional to the stability of the molecule, is directly proportional to dissociation energy, is directly proportional to lattice enthalpy, is directly proportional to bond length, inversely proportional to bond length. Here the inversely proportional to the activity, the stability is activity, inversely proportional to the reactivity of the molecule. Here the relation is bond order is inversely proportional to the bond length. Now the magnetic nature here, the two type of magnetic nature of the substance, it is diamagnetic and paramagnetic. Diamagnetic, that means here the substance which is repelled by magnetic field, or here the molecular orbital in molecule is doubly occupied, that means they have paired electron in the molecular orbital, or here the paramagnetic nature means attracted by magnetic field the molecular orbital in the molecule, one or more molecular orbital is singly occupied. That means they have unpaired electron. Paired electron, if paired electron present in all the molecular orbital, its nature is diamagnetic, and if one or more number of electron more molecular orbital and they have unpaired electron, they have unpaired electron, they they are paramagnetic in nature. Here the doubly occupied, that means paired electron, and singly occupied means here the single electron. Okay, or two electron. Here these some examples. The molecule which is diamagnetic in nature: lithium 2, carbon 2, hydrogen H2, or nitrogen molecule, or the paramagnetic, here the oxygen molecule is paramagnetic in nature. Now let's see how they are diamagnetic in nature or the paramagnetic in nature, or they are stable or unstable. Now the next concept is the bonding in some homonuclear diatomic molecules. First of all, let's see about hydrogen molecule. Here we have two systems: the order of energy of molecular orbital for 14 or less than 14 electron containing system, and the order of energy of molecular orbital is more than 14 electron containing system. Here in case of the hydrogen molecule, is hydrogen molecule, and it is formed by combining two hydrogen atom. Here the atomic number of hydrogen is 1 and its electronic configuration is 1s1. Okay, so according to the system, 4 14 or less than 14 electron system, or here the 4 more than 14 electron system, hydrogen has 1 electron. So now the order of energy of molecular orbital, here the only 1 electron is here, and okay, let's see in the diagram. First of all, in hydrogen molecule, its atomic number is 1. So here we have two hydrogen atom and its electronic configuration is 1s1. one electron and here the one electron. So bonding orbital, the number of electron here 1 and 2. Okay, and here for the hydrogen molecule it is sigma 1s 2. That means here its number of electron present in the bonding orbitals are 2 electrons only, and the number of electron present in Na is 0 because here there is no electron, 0 electron. Now from this data we can easily calculate the bond order. Bond order is equal to Nb minus Na divided by 2. Nb is equal to 2 minus 0. Here 2 divided by 2 equal to 1. Its bond order is 1. That means bond order is 1. That means there is single bond exists between the hydrogen atom. Single bond between two hydrogen atom. And the second thing is its Nb is greater than Na, then and then it is positive bond order. Positive bond order, and the molecule is stable molecule. So here we can easily write down for the hydrogen molecule this one, here the sigma 1s 2, and Nb is equal to here only the 2 electrons and Na is equal to 0 electron. Nb is greater than Na. Now the bond order is equal to Nb minus Na divided by 2, 2 minus 0 divided by 2. Its bond order is 1. If bond order is 1, then and then this single bond between two hydrogen atom, and here the positive bond order, then molecule is stable. Now let's see about Li2 lithium molecule. Here the lithium molecule is formed by combining of two lithium atom. For lithium its atomic number is 3, so its electronic configuration is 1s2 and 2s1. Now is the diagram, and here the lithium molecule, and it's 1s2 2s1. That means here in 1s orbital there are 2 electrons. Here instead of hydrogen it's lithium atom. Here 1 electron, and now 1 electron in the antibonding molecular orbital, and 1 electron present in 2s orbital, and by combining this 2 electron present in sigma 2s orbital, it's bonding molecular orbital. Now the calculation for the electron present in the bonding electron present in bonding molecular orbital and Na electron present in antibonding molecular orbital. Here in bonding molecular orbital 2 plus 2, 4 electrons. In antibonding 2, and here only the 2 electrons. Now the bond order equal to Nb minus Na divided by 2, 4 minus 2 divided by 2, 2 by 2, its bond order is also 1. Here according to the bond order 1, here the single bond between two lithium atom, and second thing is either molecule is stable or unstable. This depends upon the number of electron present in bonding orbital and antibonding molecular orbital. Here the Nb is greater than Na, that means we get the positive bond order, then and then the molecule is stable. Now let's see about He2 molecule. It is exist or not. How we can say, here the helium molecule, 2 helium atom, and the atomic number of helium is 1. Sorry, here the 2, 1. Now its electronic configuration is 1s2. So here we have only 2 plus 2 electron, that means 4 electron. Now here the 1s or helium atom, the number of electron present, 2 electrons in 1s orbital only. So in bonding molecular orbital there are 2 electrons, and here in antibonding molecular orbital there are 2 electrons. So here in electron present in bonding molecular orbital, here the 2 electrons, and Na electron present in antibonding molecular orbital is also 2. Now the bond order is equal to Nb minus Na divided by 2. Here the 2 minus 2 divided by 2, 0 by 2. Bond order is 0. And second thing is Nb is equal to Na, that means here the 0, and it is this molecule does not exist because there is no bond order. Bond order is 0. So He2 molecule does not exist. Now in C2 molecule, C2 is 2 carbon atom. For one carbon atom, its electron atomic number is 6, 1s2, 2s2 and 2p2. 1 2 3 sorry 2 plus 2 plus 2, there are 6 electron, and here the 6 electron, that means total 12 electron. So we have the diagram about the 14 or less than 14 electron system. Now here for the carbon atom, for carbon atom 1s2, 2s2 and 2p2. In 1s orbital there are 2 electrons. Now in 2s orbital there are 2 electrons, 1 and 2. 1 electrons in bonding 2s orbital, and 1 electron in antibonding sigma antibonding 2s orbital. Now the 2 electrons in 2p orbital, in px 1 electron, and in py orbital. Here by from px 1 electron, and here the 1 electron from py and py. Now for the electron present in bonding molecular orbital or NB, here the orbitals are for NB sigma 1s, sigma sorry here is sigma 2s, 2 electrons, and then pi to px, pi to px equal to pi to py, and they have 2 electrons. So total number of electrons 2 plus 2 4 plus 2 plus 2, total 8 electrons. Now electron present in antibonding molecular orbital. Antibonding molecular orbitals sigma antibonding 2s, here sigma antibonding 1s and sigma antibonding 2s. There is no electron in sigma pi antibonding or sigma antibonding, 2 electrons, that means here total 4 electrons. Now the bond order is equal to Nb minus Na divided by 2. Nb 8 electrons, 8 minus 4 divided by 2, 4 by 2 equal to 2. Bond order is 2. Then between 2 carbon atom there is double bond. And second thing, here the Nb is greater than Na, that means here the positive bond order and the molecule is stable. And now let's see the here in C2 molecule, it is diamagnetic or paramagnetic? In nature, how we can say here, the and bonding molecular orbital, there are double electron or two electrons, that means they have the paired electron, here the paired electron. So whenever the paired electron in molecular orbital, they are diamagnetic in nature. So C2 molecule is diamagnetic in nature. Here suppose the He2 molecule, it is diamagnetic or paramagnetic. Here the two electron present in one s, that means here one is sigma, one is, and the sigma antibonding one is orbital. There is paired electron in the molecular orbital, so it is also diamagnetic in nature. Here a lithium molecule, it is diamagnetic or paramagnetic. So in lithium molecule, sigma 1s2, sigma antibonding 1s2, and here the sigma 2s, and there is all the electrons are paired, and this is diamagnetic in nature. Here the paired electron, or here in case of hydrogen molecule, sigma 1s and sigma antibonding 1s, sorry, here only the sigma 1s orbital exists, is paired electron in molecular orbital, it is diamagnetic in nature. Now let's see about the nitrogen molecule. Here the nitrogen molecule is formed by combining of two nitrogen atom and their atomic number is 7. So its electronic configuration is 1s2, 2s2 and 2p3. Here the 7 plus 7, total 14 electrons present in nitrogen molecule. Now according to the order of energy, here the order of energy, 2 electron present in the sigma 1s orbital, 2 electron present in sigma antibonding 2s orbital. Here suppose it is nitrogen atom, then here suppose this nitrogen and 1s2, 2s2 and 2p3, 2 electron present in 2s orbital and the 3 electron present in 2p orbital. 1 1 2 3. Here the 1 electron from 2px and 2px, 1 electron from 2py, and now 1 electron from pz orbital. Okay, so here the number of electron present in the bonding molecular orbital. Here this bonding molecular orbital sigma 1s, sigma 2s, sigma 1s, 2s, and here the pi 2px and pi 2py, pi 2px and pi 2py, and then sigma 2pz, sigma 2pz, and the number of electrons are 2. Here also 2 electrons, 2 electrons, and here the 2 electrons. A total number of electrons here 1 2 3 4 5, 5 multiplied by 2, 10 electrons. Now number of electron present in antibonding molecular orbital. The molecular orbitals sigma antibonding 1s, sigma antibonding 2s, here sigma 2, sigma antibonding 2s, and there is no electrons, so in only here the 2 total 4 electrons. So bond order is Nb minus Na divided by 2. Nb 10, Na 4 divided by 2, 6 divided by 3, sorry 2. That means bond order is 3. If bond order is 3, that means there is triple bond present in nitrogen molecule. Second thing is here the Nb is greater than Na. Here the positive bond order molecule is stable. So nitrogen molecule, here the 2 pi bond present, here the 2 pi bond present, and one is sigma, 1 sigma plus 2 pi bond present in the nitrogen molecule. Now the diamagnetic nature or the paramagnetic nature. Here the all the electrons present in the molecular orbitals are doubly occupied. They are paired electron. So it is diamagnetic in nature. Now for oxygen molecule, here the oxygen molecule, its atomic number is 8. The total number of electrons 8 plus 8 equal to 16 electrons. Electronic configuration of oxygen is 1s2, 2s2 and 2p4. Here px, py and pz orbital 1, 2, 3 and 4 electrons. This is the electronic configuration of oxygen atom. Now we have 16 electrons. So diagram or the order of energy is change. This is only the diagram for 14 or less than 14 electron system. So now we have 16 electrons. So this diagram will not help us to find out the number of electrons present in bonding molecular orbital and the anti-bonding molecular orbital. So we have another diagram, and the diagram is molecular orbital for diagram for more than 14 electron system. More than 14 electron system. Here for oxygen atom 1s2, 2s2 and 2p4. 2 electron present in 1s, then 2 electron present in 2s orbital, and now 4 electron present in 2p. 1, 2, 3, 4 electron. Here 1, 2, 3 and 4 electrons. Is the order of the energy. Bonding molecular orbital 1 electron. Here also the 1 electron. Now in 2s 1 electron. Here in anti-bonding 1 electron, so total 2 electron. Now from 2pz orbital 1 electron enters, then 1 electron, and here the single electron in pi anti-bonding to px and pi anti-bonding to py. This 1 electron. Now the calculation for the number of electron present in bonding molecular orbital and anti-bonding molecular orbital. Here sigma 1s, sigma 2s, and then sigma 2pz, then pi 2px equal to pi 2py, and here the anti-bonding. In bonding molecular orbital there is 2 electron. Here the 2 electrons. Then in sigma 2pz there are 2 electrons. In pi 2px and pi 2py there are 2 electrons. Total number of electron 1, 2, 3, 4, 5. 5 multiplied by 2, 8 electrons. 10 electrons. And then electron present in anti-bonding molecular orbital. The anti-bonding molecular orbitals are sigma anti-bonding 1s, sigma anti-bonding 2s, and then here is pi anti-bonding 2px equal to pi anti-bonding 2py. Pi anti-bonding 1s 1 electron, 2 electron, here the 2 electron also. Now in pi antibonding to px, 1 electron, here the 1 electron, so 1 and the 1 electrons, total 4, 5 and 6 electron. Now the bond order, Nb minus Na divided by 2, Nb is 10 electron minus 6 divided by 2, 4 divided by 2, bond order is 2. That means if bond order is 2, there is double bond present in the oxygen molecule. Now Nb is greater than Na, is positive bond order. The positive bond order, this molecule is stable. Now let's check it, either it is diamagnetic or paramagnetic. In nature it is diamagnetic or paramagnetic. Here in case of oxygen molecule, here the 2 unpaired electron present in antibonding molecular orbital, and because of this it is paramagnetic in nature. Here the unpaired electron in antibonding molecular orbital, and because of this it is paramagnetic in nature. Okay friends, so this is the concept about the diamagnetic and paramagnetic nature of the molecule and their existence. Next time we will discuss another topic. Thank you very much.